Okay, I think we get started, huh? All right. Good morning, everybody. Let's see here. A note on chapter 6. I don't think we're going to get there today. I think we're going to finish 5. But if you could print chapter 6 in color or some of the pages, because hey, it talks about color and it's hard to talk about color if it's not printed in color. So I'll give you an example. Here is page 3. Maybe you could, if you have access to a color printer somewhere, print a couple extras. Here it's talking about color again. So, and color again. So if maybe the first few pages, here's some color again. So, and color again. So it's talking about color, maybe the first 10, 11 pages, and maybe you can go to black and white. I don't know. But if you get a hold of a color printer, there's one at work. Your person next door has one, buy them a drink, get them let them print in color. I don't know. Steal their printer. You have the key to their place, break in. I don't know, print in color. It would help. Okay, let's see on the quiz here. We are looking at 8. All right. So in 8, how much heat is needed to be removed from 100 grams of 85-degree water to make ice at -5? Okay. So let's do our phase changes up here. First of all, we have water, liquid at 85 degrees Celsius. I've got a good idea here. We're just going to do our arrows up here, and I think we can put our formulas up here as well. We need to cool this down to liquid water at 0 degrees Celsius, right? The very first thing we're going to do is we need to cool down liquid water. This is going to be Q is equal to MC delta T. Then we've got to take the liquid water to solid water at 0 degrees Celsius. Right? We're going to freeze it. That part right here is Q is equal to M times the enthalpy of fusion. And one more step is we have to take the solid ice at 0 to solid ice at -5 degrees Celsius. And this is going to be Q is equal to M, C for ice, delta T, and delta T is going to be 5 degrees. So this actually is a pretty good way to do it every time you draw an arrow. And then we're going to have to add up these 3 Q heat values, right? So here, this is just going to be, this looks like it's in kilocalories. You can always convert at the end. 4.184 joules equals 1 calorie. So it depends on what you use for C. You might do that conversion at the end. So you got to calculate these 3, add them up. Should do it. Number 9, a person makes iced tea by adding 1,800 grams of hot tea initially at 80 Ooh, how many kilograms of ice are required to end up at 10? Okay. Let me see. Let me see if I can do a little drawing over here. So to get a picture of what we're looking at here. We've got 1,800 grams of tea, which is just going to be water solution. And this is at 80 degrees Celsius. And we're going to add how many kilograms of ice? Whoa. We're going to drop ice in here till we get, and the ice is at 0 degrees Celsius. So that T final is 10 degrees for everything. So we've got 1,800 grams of tea. It's at 80 degrees. We want to know what mass of ice we need to drop in here so that the final temperature is 10. And we know that the ice is going to lose heat. Or excuse me, the ice is going to gain heat. Sorry. This is going to lose heat, right? It's going to become colder. So now we're going to do Q lost equals Q gain on this. Know that this MC delta T here and what's going to gain heat is going to be the ice, right? But we need to figure out this. But what has to happen is this. First of all, there's two things going on with the ice. It's at 0. So we have to melt the ice. So the first thing we're going to have to do is melt the ice, right? So that is going to be H2O solid at 0 degrees Celsius. To H2O liquid at 0 degrees Celsius. Oops. Plus, we have to heat that melted ice up to 10, right? The final temperature of this whole thing is 10, but you can't get the dropped in ice to count towards 10 degrees until you melt it all. So now we're going to heat to 10 degrees Celsius on this. And just do my arrow here. So now we're going to have to go up to H2O at 10 degrees for the ice. So again, my 1,800 grams is going to lose heat. It's going to go down to 10 degrees. That heat energy is going to go into melting the ice and then getting that ice up to 10. And we want the mass of the ice. So let's put this in here. I'm going to start over here and maybe get a number here. So this is 1,800 grams. 4.184 joules per gram degrees Celsius. Zoom in. So my temperature change here is going to be 80 minus 10. I know that's in degrees Celsius. I'm trying to save a little bit of room. Now over here. This is going to be to melt my ice. It's at 0. This is going to be my mass of ice, which I'm looking for, times the enthalpy of fusion. That's how much heat energy is to melt my ice. Now I need to raise that. I have it at a liquid at 0. I need to raise it up to 10. So this is going to be plus my mass of ice. Now it's not ice at this time, right? It's really not ice at this time, but I'm going to leave M ice because it's the same number there. Mass of ice times my specific heat. It's liquid water now, 4.184. Then my temperature change here is 10 degrees, right? 0 up to 10. I could go 10 minus 0. So now out of all that, you want to solve that for the mass of ice. Now the easy way to do it might be to factor it out. If you're not comfortable with that, stick your enthalpy of fusion in there and combine the like terms, mass of ice, and solve it. If you're looking for mass of ice, if you're using grams here and enthalpy of fusion, use it in joules per gram. You're gonna have to convert to kilograms at the end. So you want to solve that for your mass of ice. 11. In 11, how much heat in kilocalories is needed to melt 10 kilograms? And we're going to melt 10,000 grams of aluminum. Initial temperature is 30 degrees. Well, we can't melt it. All we need to do is melt it. So here's what we need to do. We have aluminum, solid. It is at 30 degrees Celsius. We need to get aluminum. It's a melting temperature, which looks to be 660. So the first thing we need to do is take this chunk of aluminum. It's pretty much at room temperature. It's in a warm room, 85, 90 degrees Fahrenheit. It's kind of warm. We need to get it from 30 to 660 degrees Celsius. And that calculation there is going to be Q is equal to MC delta T. Oops, I forgot to put solid. Solid. Now we need to take that solid and turn it into aluminum liquid at 660 degrees. All we got to do is melt it. So this is going to be Q is equal to M times the enthalpy of fusion. And it looks like these are given, everything's given in calories. So you're just going to have to change to kilocalories when you're done. Looks like we're given everything. The specific heat of aluminum is 0.215. And yeah, enthalpy of fusion is given there. So I think you can finish that. Right, and then you're just going to add these two up. You're just going to add these two up then, right? To get the total heat. Okay. Let's see, is that it? Yes. Let's see what we're going to do here coming up. Got a blue pen up here, another pen, an extra pen they would throw. Somebody got a blue. Start with, is it smooth pen? Okay, at least I have two colors. All right, let's see where we left off. We are going to work on so we left off with the first law of thermodynamics, and we went through some specific OWL questions concerning heat and work. We are now going to do what's called the enthalpy of reaction, or the heat that we get out of a reaction, or the heat we have to put in to complete a reaction. So here's some examples, and then we'll have some OWL examples as well. So we're doing reaction heat now. We're doing reaction heat. What do we use for a symbol? Delta H is the enthalpy of, R is reaction. This little symbol means at standard conditions. Typically, this is 25 degrees Celsius, which is about room temperature and about in 1 atmosphere of pressure. So this says if we combine hydrogen plus a half of oxygen to give us a water that's still balanced, and this phase matters, it's a gas, we should get 241.8 kilojoules per mole. This negative right here means that this is exothermic. Heat is a product. So another way you could see this reaction is we could go H2 gas plus 1/2 O2 gas H2O gas. They would just put plus, it's going to be on the product side, 241.8 kilojoules per mole. So you might see this, it's negative here, heat is given off as a product. And another word for heat given off is energy is evolved. So in this balanced equation, there's a 1 right here, right? That we don't write. Oops, sorry. So now it says, if you had 2 moles of hydrogen, then you would get double the energy out, which makes sense. It's kilojoules per mole. And if we ran a 2 through this equation, I went back here and did this. And we're setting you up to do the next type of problems. If I run a 2, I'm just multiplying the 2 all the way through there. So 2 times 1 is 2. 2 times a half is 2/2 or a 1, right? 2 times 1 there, I would get a 2, and I simply double my heat I would get out. I'm just multiplying everything through by 2, including my enthalpy of reaction. Okay. So if we double that, we double the heat. Now let's look at this problem here. I should probably say we multiplied this by 2. I mean, we literally multiply everything by 2. Now I have note, state, solid, liquid, gas, matter. This time, instead of a gas, I have a liquid. it is still exothermic, right? We get heat out, we get a little bit more energy out if we create a liquid. So now, if you reverse the above reaction, the enthalpy of reaction values would be opposite signed. In this case, all positive. So if we reverse this reaction, let's draw it out. Let's do it right here. If we write this out in reverse. So instead of having water, I'm just going to write reverse right here. This is the reaction. Instead of having water as a product, we would have to have water as a reactant. We got to put in the L for liquid. We draw our arrow. We're just reversing this reaction. And now hydrogen gas is here, plus 1/2 oxygen gas. And this is the key. Instead of this being negative, instead of getting heat out, we're going to have to put this heat in. This is the key going forward. My enthalpy of reaction is now going to be positive 285.8 kilojoules per mole. If you reverse the reaction, change sign. Again, negative to positive. I can put a plus there, I guess, to overemphasize it, but a plus. Okay, and that would make sense. I mean, instead of getting energy out, we're going to put energy in if we reverse it. So let's do the next couple examples. The standard molar enthalpy of combustion. This is a combustion reaction. This is propane. Unfortunately, the weather's going to change. We're going to be burning a lot of propane coming up. It says the standard molar enthalpy of combustion for propane is negative 2044 kilojoules. What is the standard enthalpy change for the combustion of 3 moles of propane? Well, if we multiplied this whole thing by 3 again, we're going to multiply this times 3. And we are simply going to get 6132 kilojoules. You're going to see more applications coming up before we're done today of reversing reactions and multiplying them. Okay, here's an example 5,6. Table sugar can be oxidized to carbon dioxide and water, and the enthalpy change for the reaction measured is negative 5645 kilojoules per mole. This is for a mole of sugar. One mole of sugar. Now, what is the enthalpy change when 5 grams of sugar is burned? No formula needed here. If you're given grams of sugar, 99 times out of 100, if you're given grams, what should you do? Convert to moles, right? So that's the very first step we are going to do. So we've got 5 grams. Grams to moles. Then we want to know how many kilojoules we're going to get out. We can bring this down right here. We're looking for kilojoules. I can just put this in as is, right? Because my moles are going to cancel out. This is kilojoules per mole. So I can put this in as negative 5645 kilojoules per mole. That is per 1 mole of sugar. So we don't have close to a mole. I mean, a mole is 342.34 grams. We only have 5 grams. We're still going to get some heat energy out of this. And the amount of heat energy out we would get is negative 80. Anybody running this through? Negative 82.4. Okay. Now the next one's going to have a little bit of a twist, not much. What is the enthalpy change for 15 grams of C2H6? But notice right here, this is how many kilojoules we get out for. We're going to make sure we use that at the end. This is how much heat energy we get out, but this takes 2 moles to do it. So we're going to do the same thing, 15 grams. The moles. $2430.08. It that's how many kilojoules we get out if we add 2 moles. to me, it would kind of be ideal. You can run a 1/2 through this equation, then you would have half of this, then it'd be for 1 mole. To me, it'd make more sense, but we just got to make sure this amount of energy given off is when you burn 2 moles. So we just take that into account right here. And then the amount of energy we would get out of this is -712. All right. Here's, I believe, this last type of question. Yeah. So if we have this reaction, same ones up above, this involves 2 moles here, 7 moles of oxygen, 4 moles of carbon dioxide, 6 moles of water produced, and the enthalpy of reaction is -2857.3 kilojoules per mole. This time, if you wanted to release this much energy, want to release, the key word is making that negative then. We're looking for grams. No formula here. Let's see. We need grams. If we can get the moles, we can get the grams, right? Where do you got to start? This is a single unit number. Look at my double unit number. This is in kilojoules per mole, right? So we're going to start with our single unit number. We're going to get kilojoules to cancel out. We always start with a single unit number. So let's start here with -775 kilojoules. Now we're going to bring this down right here. I'm trying to draw an arrow, trying to make this look decent. Here comes my arrow. I'm going to go up way over here, way underneath here. And I also need to do this. I need to flip the units, right? I'm going to flip the units. I'm not going to put in kilojoules per mole. I'd end up with kilojoules squared. I'm going to flip my units to get them to cancel out. So first off, I'm going to put my -2857.3 kilojoules there. I take into account the balanced equation here. Two. Now we can just do 1 mole of C2H6, 30.08 grams. Okay. All right, let's go to the next page here. All of this is for our next lab on heat coming up. So this week, we did the stoichiometry for generating carbon dioxide gas. The following lab then is doing heat. And it is really this. So 5.7 is enthalpy calculations for reactions, actually calculating now how much heat we can get off. But we use Hess's law for reactions that are too dangerous to run. Or we simply do not have reagents, maybe. Okay. So Hess's law is just adding reactions together, kind of like algebra, canceling X common terms on both sides. So we're using, in this case, we'll show you this example, we're using these two reactions, this reaction. So let's say this reaction is too dangerous to run. We don't have the ability to do it. We can combine these two reactions to figure out how much heat we would get for this one. Okay, Hess's law is just manipulating. We're going to reverse reactions. We're going to multiply and stuff like that. So first of all, take a highlighter and realize this. We want H2O liquid on the product side, and we want H2O gas on the reactant side. And we come down here, here's our H2O gas here. Here's our H2O liquid here. So what we are going to do is we're going to manipulate these two equations so it adds up to this one. So the first thing you notice, this is what you want to do in highlighter. I'd have highlighters for these. You're going to want highlighters for these. Anything that's not highlighted has to cancel out. So we just like canceling out for net ionic reactions. We need to get oxygen on a product side and oxygen on the reactant side. So they cancel out. So the very first thing is, this reaction right here needs to be reversed. Because I have H2O gas, I need H2O gas on the reactant side. So the very first thing we are going to do is, I'll draw an arrow. We'll work it out right here. We're going to reverse this reaction. So we're going to reverse this reaction. So we are going to have 2 H2O gas. And we're going to have 2 H2 gas. Plus O2 gas. And if we reverse it, This is going to become positive, right? Kind of ran out of room. This is going to be positive 483.6 kilojoules when we reverse it. I want to stick it right here. So that's nothing new. We just reverse the reaction. We have to reverse the amount of heat. And now I have H2O gas. I wonder if this is going to smear. It doesn't at all. There's my H2O gas. I am going to bring this one over, and I'm not going to change anything. It's going to be the same. Let's see if I get off. So I'm just going to write it as is. We have 2 H2 gas plus O2 gas. Get 2 H2O liquid. And my heat stays the same, negative. I'm going to draw a line. H2O liquid is over here. I'm going to highlight that again. The rest should cancel out then. And they do. I have 2 H2O. I have 2 H2 gas. I'm going to put a light X here. And I have O2 gas as a product, and I have O2 gas as a reactant. I'll put a light X over them. And now I have 2 H2O gas going to 2 H2O liquid. And my heat is going to be for 83.6 kilojoules and a negative 571.7 kilojoules. So my enthalpy of reaction is 88.1. Okay, again, we're using these two reactions to get this reaction that we did not have the reagents to do. It's too dangerous to run. So we can combine reactions to get the one we're looking for. Now, Al starts out, it just does some simple stuff. What Al will do is, let's say Al gives you this reaction. Yes. Oh, because I forgot to put the negative in. Good question. It should be negative, yes. Throw something at me. So Al starts out, it's just going to say, what would be the enthalpy change if you doubled this? So it's going to be double this number, right? Or Al's going to start out, what's going to be the enthalpy change if we reverse this reaction? So you're going to make it positive. So Al starts out, it doesn't start out by combining like this. It just starts out with some simple questions. Then it does this combination. Okay, another combination then, get your highlighters out. Let's see what we got. We're going to need 3 colors. And the reaction involves P4 solid on the reactant side. So that looks good so far. I like what I see so far. We need P4 solid on the reactant side, and this first equation has it on the reactant side. That's good. We've got PCl3 liquid on the product side. Ew, I don't like this because here it's on the reactant side. And Cl2 gas is on the reactant side, and it is in two places. That means this we're going to eliminate. Plus, we need a 4 here, right? I kind of like what I see though. Think about this now. We do not have a 4 here. We're going to have to multiply this one by 4. But if I multiply it by 4 and reverse it, 4 on the other side, 10 on this side should give me 6, huh? All right, so I left enough room. I got a little smarter here. Let's do this first. We're going to bring this down. And we are going to go reverse times 4, all in one shot. Reverse times 4. Okay, so I'm going to bring the PCl5 solid on the reactant side now, and I'm going to have a 4. PCl5 solid. PCl3 liquid. Ooh, I didn't keep my colors. Cl2 gas. Now, this is going to be 4 times a positive 123.8 kilojoules. The negative becomes positive because we reversed it, right? But I've still got my 4 there. If I do my colors, I've got this over here, which I like. I've still got Cl2 here. And we should be able to just bring this one down. I'm just going to rewrite it because then it's going to look better. This is just going to stay the same, right? This can stay the same. And we're going to have P4 solid plus 10 Cl2 gas. L5 solid. And this is going to be negative 1774.0 kilojoules. Cl2 gas. P4 is in pink. So the highlighting helps a lot, especially we're going to end up adding 3 equations coming up. So we're going to draw my line and add these up. So if I draw my line here, anything that's not highlighted should cancel out, and it does. First of all, we'll put a light X because we've got 4 PCl5 solids and 4 PCl5 solids. So we'll lightly X those out. Now, 10 on the reactant side, 4 on the product side becomes 6 on the reactant side, right? We're going to eliminate 4 out of these 10. 4 here, 10 here, leaves me with 6 Cl2 gas, right? And we've got P4 solid plus 6 Cl2 gas, arrow. And I've still got my 4 Cl3 liquid. I'm going to add this up. And when I add this up, I'm going to get 1278.8 kilojoules. Yes. 4 PCl3. Yeah, I'm missing my P, aren't I? That's not very good. Right there. Now, let's say you added this all up, and let's say this was a 2, this is a 12, and this was an 8. That's fine. You can just divide everything through by 2. If it doesn't come out perfect, but if you look at this, you've added them all up, and you look up here and go, oh, crap. If I just take half of this, it works. You can do that. You can just run a half through that, and then if it matches up that. Okay. How are we doing on this? You're just kind of playing a game, huh? It's not overly difficult. You just got to, because you can do it many ways. There's more than one way to do this, especially as we go forward on the next page. So let's figure out what we got here. Let's highlight this. We want nitrogen gas on the reactant side. And right away, I'm pretty happy because I've got nitrogen gas on the reactant side. And the number matches, right? 1 and 1. So right now, I'm thinking, I shouldn't think there's way. This might be an easy problem. Then it comes back to bite me. Now, let's take another highlighter. We've got NO2 gas on the product side. I've got NO2 gas on the product side, but this one has a 2, right? But right now, I'm thinking if I multiply a 2 through this, it would match up. And then we've got O2 gas here on the reactant side. Ooh, we got them on both again. But I'm liking what I'm seeing. Hopefully your brain's moving here. You're putting this together like a Sudoku, huh? I don't know. Really now, the only thing we have to do is do what? All we're going to do is multiply a 2 through this one, right? So this is going to stay the same. I'm just going to write same. And this one, we're just going to multiply a 2 through here. I'm going to do it right here. I'm going to put a 2 there. I'm going to put, if I go 2 times a half, it's 2 over 2, which is 1, right? I'm going to put a 2 here. I'm going to put a 2 here. And I'm going to go times 2 here. I'm going to draw my line, and this one's going to be done. Because now I've got my 2 NO gas, it has to cancel out, right? Remember, anything that's not highlighted should cancel, so I can cancel this. I've got N2 gas plus. This is an O2 plus an O2, right? 2 over 2 is 1 O2, so this becomes 1 O2 plus 1 O2 is 2 NO2 gas. Two NO2 gas. If I add this up, they're going to be positive, not by them. So we're going to, if we multiply this by 2, that's about a negative 114. So we still get a positive 66.4 kilojoules. Yes. Say that louder, please. Why is there 2 oxygen? Okay. This is 1 oxygen, right? And this 2 times a half, I should put it like this. If I put this like this, and I zoom in here, it's 2 times a half is 2 over 2 or 1 oxygen as well. So I'm getting my 1 oxygen there plus my 1 oxygen here for my 2 oxygen. Yes. Say that louder. Yep. Last part. Yep. Yeah, if it's on opposite sides, we're going to cross it out. But if it's on the same side, we need to add it on. Yeah, we're going to add it if it's on the same side. If it's on the opposite sides, we're going to cross it out. So again, this right here is 2 times 1/2 oxygen. And 2 times a half is 2 over 2, which is just 1. Let's go to the next page. We're going to saddle up a bigger horse because now we've got 3 reactions. All right, get your highlighters out. We've got carbon solid there by itself on the reactant side. We've got carbon solid here. I like that. It looks good. We don't have to do anything. We've got H2 on the reactant side. We've got H2 on the reactant side, and the number matches. I like that. Except it looks like we might have to multiply a 2 through this, right? Because we've got a 2 H2 here, but we only have 1 there. So far, I'm looking like we're going to have to multiply this one through by 2. And what does this look like? We have CH4 gas. Where is that? Ooh, we're fine. We're going to end up reversing this one, right? Reversing the third one, multiplying the second one by 2. It looks like that's all we have to do. So let's go ahead and do that. To make this look nice, we'll do this one first. And we're just going to reverse this. We reverse this. You're going to have the CO2 gas plus H2O liquid. You're going to get CH4 gas plus 2O2 gas. And so we reversed it. This is going to be positive 890.3 kilojoules. And we reversed it. This looks nice. We got our CH4 on the product side, right? Which matches up above. Now, reaction 2, what do we need to do to this? You're just going to multiply it by 2, right? There's a 2 right here that we don't have, so we're going to multiply everything through by 2. I wish I can try it. Colors don't show up. 2 times H2 gas plus 2 times 1/2 O2 gas water liquids then 2, we didn't reverse this, did we? 2 times negative 285.8 kilojoules. So we're not changing the sign because we didn't reverse it, right? We're just multiplying. Here's my 2. I just carried a 2 all the way through. And I'm hoping that this one right here can just stay the same, right? So where's my highlighter? My blue is my H2 gas right here. There's my blue, which matches up above, the number matches. And here we're going to leave it the same. Carbon solid, O2 gas, carbon dioxide gas, and we leave it the same. This is going to be negative 393.5 kilojoules. This was in yellow. Now, everything else has to cancel out. Whatever I do not have highlighted, this should work because I have an exact match. I've got 1 CH4 here. I've got 2 H2 here. I've got 1 carbon solid there. Everything else should cancel out that is not highlighted. So see what we got here. Whew. We got a carbon, this one's an easy one. We got a carbon dioxide gas and a carbon dioxide gas here we can eliminate. Put a slight X here. Now, all right, this is going to work. We've got 2 O2 gas there, and maybe I should highlight this with a color I have not used. This 2 O2 gas comes from 2 times 1/2 is a 1, and there's also a 1 right there, right? So we have 2 O2 gas on the product side. This is 1 O2 gas and 1 O2 gas. So this is going to be eliminated. This adds up to 2 on the reactant side. And why do I have an extra water here? What did I miss? I missed this 2. When I reversed this, I did not put this 2 in here, right? So we need to put this 2 right here. And now that cancels out as well. So make sure you stick that 2 right there, otherwise, woo. So then we have it, we can add them up. I guess I can write it out. Carbon solid, 2 H2 gas, CH4 gas. And if I add all of this up, negative 74.8 kilojoules. Again, for lab, we're going to add up two reactions. We're going to measure the heat given off, and we're going to add up two reactions to get the heat value for a reaction that we did not run for lab. Okay, one more, and that is 3 of them here again. Let's highlight, see what we like. CLF gas. And only a CLF gas. Where is that thing? Right here. This is the only place that is. Right now, since there's a 1 here and a 2 here, I'm thinking I'm going to divide this or run a 1/2 all the way through this one, take half of it, or divide by 2 all the way through. That's what I'm thinking I'm going to have to do. But we'll see. F2 is right here, and that's 1 F2, but this is a 2 F2. Oh man, and it's on the wrong side, right? So right now I'm thinking I'm going to reverse this and divide everything by 2, right? Ooh. Now, can we get, are any of them going to come out nice? CLF3. I've got 1 CLF3, and it's right there. Well, it looks like nothing's going to stay the same on this, huh? The rest of this should cancel out. Now, to make this, what am I going to have to do with this reaction? We're just going to reverse this, right? So we're going to reverse this pig. All right. So reverse this. I'm going to have 1/2 L2O gas plus 3/2 OF2 gas. This is ugly. I've got CLF3 gas plus O2 gas. This one is going to become negative 266.7 kilojoules. I don't know, this horse is a Clydesdale we saddled up this time. This is a big horse we saddled up. Ooh. All right, we had to reverse this. I didn't even write that down there. Come on, get reverse, right? All we did was reverse. Yes. Okay. For the next part here, what do we got to do with reaction 2? What did we figure? For reaction 2, it looks like we just got to multiply it by 1/2, right? Because we have a 2 here, but we only need a 1. So I like to say times 1/2, it's the same as dividing by 2. So that means I'm going to have 1/2 times 2 CLF gas plus 1/2 O2 gas. Wow. This is getting uglier instead of prettier. I'm just multiplying. I'm putting a 1/2 in front of everything, right? I took a 1/2 of everything all the way through. Ooh, number 1. What are we going to do with reaction 1? We're going to reverse it, correct? Because we need the F2 on the other side. And we're also going to do what? Yeah, we're going to reverse times a 1/2, reverse times a half, reverse times a half. So let's see. So I'm going to have 1/2 O2 gas plus 1/2 2 F2 gas, 1/2 OF2 gas. That's reversed. And now I got to take 1/2 of the opposite sign of that. So 49.4. Now I'm hoping I can draw my line. Just find everything again. There's my F2. ELF3 better be over here, and it is right there. My F2 is, oh, I already highlighted that. My CLF, where's my C? Right here. At this point, the rest has to cancel out unless I missed a number like I did last time. There's nothing pretty about this, but I think we got it, huh? I mean, it's not difficult. Kind of playing a little game, kind of. So let's see what we got here. We got 1/2 Cl2O. Where's my other 1/2? 1/2 Cl2O right here. I'm going to kind of indicate this as best I can. This is going to cancel out. Those two are going to cancel out. I have, here is my 1/2 O2. I can use a color I haven't used. 1/2 O2 plus 1/2 O2 is 1 O2. That matches that. That cancels out. Okay, so that cancels out. I don't have another color to sacrifice, but I have a 1/2 OF2. I have a 1/2 OF2. And that's only one on that side. I'm missing a 1/2 OF2. What did I mess up? Because I need 1 and 1/2 on this side. What did I mess up? Right there. Right here. Yes. That should be 1/2. I missed my 2 right here, right? So I missed my 2 right here. So this is a full OF2. That's a 1/2 OF2. Gives me my 3/2 OF2. Oh, yeah, see, just one number. So if you add this up, it's there. This number here comes out to be delta H is equal to minus 139.2 kilojoules. So let's see what I have here on this. So now on the quiz, should be able to do 1 through 16 on the quiz. 1 through 16 on the quiz. For sure, next time we're in the chapter 6. That's going to be on Tuesday, and I believe the exam is a week from Tuesday. That's what's on the schedule, right? Okay, so this will work out perfect. We're going to finish up Tuesday. Do I need to change the hour deadline? I don't think so. I think the hour deadlines are correct. Okay, all right. Have a great rest of your week and weekend.